let us have a look at something which is very, very important. And this is called as a unit vector. Now, a unit vector is a vector which has magnitude of 1 unit and is also known as a directional vector. Now, why directional vector? Now, when we take, let's say, when we go to the next few slides, we will get to know that as we proceed in the chapter, a vector that is there, let's say, for instance, if I write a vector, I can always make sure that it is broken down into its components. That means yesterday when we saw position vector, we had seen that there will be a vector that is starting from the origin and joining a particular point. So this is how we had drawn it. So at this particular point, let's say point P, if I call this as the A vector, from math we know that this position is described by x, y. And that is what we are going to write our vectors in terms of x and y. So in this case, A vector is along the direction P. That is something which we can tell, but we will not be able to tell how much it has moved along the x-axis and how much it has moved along the y-axis. And that is where this unit vector comes into picture. Since its magnitude is 1, we can use it how we seem fit in a given expression. So if you have to write a unit vector, the formula is vector by magnitude of the vector. That is, the way we are going to represent a unit vector is A with a hat on top of it. And if I take the vector that is there, it is going to be A vector by the magnitude of A vector. We write it like this within the modulus sign, which means that we will take only the numerical value of A and not the direction that is there. So if we have a three-dimensional system, like how I'm just going to draw here, and if I'm going to label the axis as, let's say, x, y, and z. Now we know that x, y, and z are three mutually perpendicular axes. For instance, for us to understand, what we can do is we can take our fingers like this and align them in this particular way. So you can see that my thumb, forefinger, and the middle finger that are there are mutually perpendicular to each other. They are pointing in three different directions. So if I take this as the x-axis, I can take this as the y and take this as the z. Now that depends on how we are trying to orient. If I change the orientation like this, or let's say if I change it towards me, it is going to change. So based on that, but if you see, at any instant, these three are mutually perpendicular to each other. So along x, y, and z, we have designated unit vectors. That is, along the x-axis, we call it as I cap. Along the y-axis, it is called as j cap. And along the z-axis, it is called as k cap. So even if x, y, and z are interchanged, I will always tell or will show us that it is the unit vector along the x-axis, j is along the y-axis, and k is along the z-axis. Now, we will move on to the topic of resolution of vectors. Now, why is this very important? We have seen addition of vectors using geometry and using the triangular law of vector addition. And we also know that we can subtract vectors using, again, the triangular law or the parallelogram law or the geometrical arrangement that is there. But if you have to do it more mathematically, let's say algebraically or analytically, we would need to know how to do it. And this is how we are going to do it. So here I have a vector which is written as small a. Now this is wrong because we always associate a capital letter with the vector. So if I have a vector that is there, let me redraw the axis here for our ease. So writing this is wrong. Writing this as small a is wrong because the general nomenclature that is followed is writing a capital letter. So if this is my vector, I can go ahead and label the axis x and y. Now this point is going to be some x, y, some number. So for that, how do we determine what is x? In general, we would tell whatever distance it has traveled along the x and the y axis. So if I drop my perpendiculars here from this point onto the x and onto the y axis, I will get what is the exact value that is there. So since we are dropping perpendiculars, we need it to be dotted lines, and I will draw the dotted lines here. Yes. So this is point P x comma y. Now if I had called this as the A vector, then this distance along A for x would be ax, and the distance along y would be ay. It is saying that if this is my vector, I will take the shadow of it along the x and along the y axis. Now this is what is called as a resolution of vectors. So what have I done? I have resolved the vectors such that I have an x component and a y component of this particular vector that is there. Now the question comes, how do we write it? So the mathematical way of writing it is, I will have a vector is equal to the magnitude along x-axis into I cap plus magnitude along y-axis into j cap. So you can see here, ax will be the magnitude along x-axis, ay the magnitude of a vector along the y-axis. Now, if we have to write the unit vector, so previously we have seen that the unit vector is written as a cap is nothing but a vector by magnitude of a vector. A cap we can get from this formula. A vector I know it to be nothing but ax I cap plus ay j cap. Now how do I find the magnitude? Now to find the magnitude, it is very simple. It's how we have done the resultant. The magnitude of a vector is just going to be equal to a, which is nothing but root of ax square plus a y square. Now how do I arrive at this is, if you look at the previous diagram, this line here, that is ay, and this is symmetrical, so I can put ay here. Now using Pythagoras theorem, I can find the magnitude of a, because this is a right angled triangle. Ax square plus ay square gives us a square. This is the same thing or the same technique that we have used in finding the resultant vector when we have seen the triangular and the parallelogram law of vector addition. So I have used the same methodology here in order to arrive at this. So this becomes root of ax square plus ay square. So here we have a little more detailed diagram. Now when we look at this diagram, we can easily tell that you have ax as the length of this a vector along the x-axis. So you get ax vector is nothing but ax I cap. Now ideally we can write a vector is equal to ax vector plus ay vector. So what have I done? I have written it as ax I cap plus ay j cap, which is not wrong, but it is a different way of writing. So both these are correct. Now if you look at this, we can actually arrive at this formula, the second equation that I have written, using the unit vector understanding. Now I cap is the unit vector along x-axis. So we should write ax vector by modulus of ax vector, which is nothing but ax vector by ax, or ax vector is equal to ax I cap. So similarly, I can write what is ay vector. Ay vector would be nothing but ay j cap. So you can see that the formula is not wrong, but there are different ways of expressing it. And the theta is always measured from the x-axis. Now you can see the resultant that is there is nothing but root of ax square plus ay square, what we had written for the unit vector. So there are two ways of expressing a vector. That is, we have added both the vectors along x and the y-axis. Next, we have written them in terms of their magnitudes. Now the second equation that is there, that is this one. A vector is equal to ax I cap plus ay j cap is a more generally used expression compared to the first one that is written. Now coming to the 3 dimension, I already told that we associate x cap or the, let's say, I cap along the x-axis, the j cap along y-axis and k cap along z-axis. Now here you can see that there is a cube whose corners have taken as the x, y and z axis that is there. Now for simplicity's sake, what you can do is, if you look at your room that you're sitting in, you would have the ceiling that is there and walls that are surrounding it. So you would get this kind of a picture, either at the top, or you can look at your floor. Wherever the wall meets the floor, 2 walls are meeting the floor. So I'll write this as wall, this is the floor. This can be the ceiling. So this is the wall. So the ceiling is this. So these are 2 walls. Now each of these, if you see, you can actually understand that you have got x, y and z axis. It's a 3-dimensional figure. Now, in this case, when I have a 3-dimensional figure, how do I write the vector is the question. Because till now, when it was 2-dimension, writing the vector was very easy. But how do I write it in 3-dimension? So let us go ahead and draw an arrow. So this is my vector. The red color one is my A vector, which is along not any axis. It is not along the x, y or z axis, nor is it along the, let's say, xy, yz and zx plane. So there are 3 planes that are surrounding this vector. Now, we can use the analogy of A vector as nothing but ax I cap plus ay j cap. We can just add another axis. So I can have az k cap, which is absolutely correct. There is nothing wrong with this. Because what we have done, our understanding in 2-dimension, we have extended it to 3-dimension. So this is absolutely correct. Now another way of writing this is, we have already seen the magnitude into the unit vector gives us the vector along that axis. So I can write this as A vector is equal to ax vector plus ay vector plus az vector. And we know that the first equation, the one that I put 2 ticks, is the equation that we are going to write, which is the general form. So here you can see ay vector is written as ay j cap, ax vector is ax I cap, az vector is az k cap. So if I have to find the magnitude of our A vector, or the unit vector if I have to find, I need the magnitude first. So for this, what would be the magnitude of A vector? It would be nothing but root of ax square plus ay square plus az square. Now we are not going to derive this expression because it's an empirical relation. Since in 2-dimension we have ax I cap plus ay j cap, 3-dimension we've just added az k cap, which is absolutely correct, and the same thing goes for the magnitude. So our unit vector can now be written as A vector by magnitude of A vector, which is nothing but ax I cap plus ay j cap plus az k cap whole divided by root of ax square plus ay square plus az square. So now, since we have seen the difference of writing resolution of vectors in both the 2 and the 3-dimension, let us look at practically how it looks. More than the theory, we have to understand practically how it looks. So for that, I will take this as my A vector. So this is A vector, and you can see that it has immediately resolved itself into its components. So if I don't have the components, this is how it is going to be. Now I will give it values so that we know what is the magnitude of A vector. Now if I am writing this, so the magnitude is 14.1. We can take it in terms of meters, and I will give the angle. It is 45 degrees. Now let us resolve this A vector into its components. So the moment I resolve it, I can see that along the x-axis, its value is 10. Along the y-axis, its value is 10. That is the resoluted, let's say, components that are there. Now, I can take another vector, B vector, here. And you can see that it has taken not the origin here, but the vectors are resolved just where our vector is written. So we don't have to actually place it at the origin. We place it at the origin in a graph for us to understand that this is how it is going to vary. But in general, any vector that is kept at any point can be resolved. Let's say this is C vector. So you can see that it is pointing vertically downwards, and it is taken as a resolution of minus 90 degrees. Now I can rotate this vector, and you can see that since it is taken in the negative y-axis, the angle, it is minus 45 degrees. But otherwise, if you're taking it from the x-axis upwards towards the positive y-axis, it is plus 45. So this is how we do the measurements that are there. Now, let me again get back to vector A. So this is the components that are there. Now, what I can do is this 8 that is there. So I kept it at 45 degrees so that we could see what we get. Now, I can show it's the same thing what I had here previously, that is along the y-axis. I have just taken it here to form a triangle. Now from here we can go ahead and find tan theta. So if you look at tan theta here, tan theta will be nothing but adjacent, opposite by adjacent. So that will be 10 by 10. Tan theta is equal to 1. And we all know that for tan 45 degrees, we get the value to be equal to 1. And we can find the magnitude using this, that is 10 square plus 10 square under root. We end up getting 14.1. So this basically the simulation is giving it right away. Now let us look at addition of vectors that we've already done. So for this, let us look at A vector and B vector. Now if I'm keeping A and B vector in, let's say, the same order. So what was our triangular law of vector addition? It said that if A vector and B vector are in the same order, then the resultant has to be in the opposite order. If you see, this is going to be our resultant. So A vector and B vector are in the same order, but here the C vector that is there has to be in the opposite order. So it starts from the origin, terminates here. So this is our addition of vectors that are there. So now let us look at the addition of vectors. I am going to look at this equation, that is A plus B is equal to C. So in this A plus B is equal to C, I have got A vector, B vector and C vector. Now let us look at their values. So A vector is 5, B vector is 7.1, the magnitude, and C vector is 11.2. So if I am going to align it, A vector plus B vector, both are in the same order, you can see that my C vector is in the opposite order. I can also go ahead and increase the magnitude of A and magnitude of B. So accordingly, if I can place this, let's say this is A and B, this is going to be our C vector. Now what if I write it as A minus B is equal to C vector? That is this. I have magnitude of A as 2, magnitude of B as 2, that is what I've written here according to this equation, and this has to be equal to C. So this is how we can write. So we can see that A and B are in two different directions. So if I'm looking at the triangular law, I can say that B vector and C vector are in the same direction, and A vector is in the opposite order, or you can even put it like this. C and B are in the same order, A is in the opposite order that is there. So these are two ways in writing the equation. We can even write A plus B plus C is equal to 0. So if I look at this, what is happening? I have A which is moving upwards, B which is in this direction, and I'm telling that C is equal to 0. So what I will do is I will make this unity and I will choose the last equation. Now the way how we are going to, let's say, design this, or we are going to place these vectors, would make sure that we get the magnitude equal to 0. If I look at the values here, again these are the original magnitudes that we had seen. We can also look at the base vectors, or we can resolve them. So this would be the resolution of B vector. This is the resolution of C vector. Now A is just along the y-axis, so we cannot resolve it. So this is how the vectors are resolved, and they are written according to their components. Now we can also write it in a particular way. So if I take, let's say I place all of this aside, if I'm looking at A, and if I write the AX vector, so you can see by how much. If I think I made A vector is equal to 6.4, you can see how the C vector is changing. And these are directions which are pre-aligned. So this is along the x-axis, and if I'm going to change it along the y-axis, this is for B along x-axis I've increased. So if I place this end to end, I can place this here, and I have my triangular law of vector addition. Now here what I have done is I have changed the value of AX and AY, BX and BY, that is the components, so that we can get the final C vector. Again, we can take another example of a vector. Let's say I have placed one vector here, and this is written as V vector. Now, if I take the components of V vector, this is how the components would look along the x and the y axis. So let us take the value. So along the x-axis, the value of V, the Vx is 8. Along y-axis, Vy is 6. So therefore, the magnitude of the V vector is equal to 10. Now we can also find the angle. This is at an angle of 36.9 degrees that are there. Now if you are wondering how I got 6 and 8 without even doing the measurement, we can actually look at it like this. So what we have done, whatever we get as a component along the y-axis, we mapped it on to the y-axis here and counted the number of squares. Similarly on the x-axis, you count the number of squares, and that's how you get the magnitude. So in a graph, it is easier to find the magnitude of x and y-axis. This is in a two-dimensional system. We can do the same for a three-dimensional system also. Only thing is, there it is going to be a little more complex to determine AX, AY, AZ for A vector, and also the corresponding angles that are there. Because we have 3 planes and 3 axes, so the way how we are going to do that measurement is slightly more complex. And for our understanding of vectors that are there, we don't need that level of expertise that is there. So with the simple idea that we can have AX plus AY plus AZ, that is AX I cap plus AY j cap plus AZ k cap is equal to A vector if we have, is more than sufficient for us to solve few more concepts that are there. Now, since we have seen how we can resolve the vector into its specific components, the unit vectors that are there, we can go ahead and look at how to do vector addition using the analytical methods that are there, or analytically how we can do the vector addition. So till now, we have seen the method of adding vectors using geometry, triangular law of vector addition, parallelogram law of vector addition, and we also learned how we can resolve the vectors. Now for the analytical method that is there, we will use the resolution of vectors. Now this is a very important concept that is there. That is why we went ahead and dealt with resolution in detail. Now, so for instance, if I have got a vector, we have seen that I can write this as ax vector plus ay vector, and more commonly in terms of the unit vector, we can write this as ax I cap plus ay j cap. Note, we cannot write it as ax I cap. This is wrong. Now what we mean by ax I cap is the magnitude of a vector along the x-axis. So it has to be a subscript x, a subscript y. Don't have to write it a into x. A into x is a completely different thing. So similarly, if I look at b vector, I can write this as bx I cap plus by j cap. Now what is the point of doing this? Now we know that the resultant, if I'm going to write, is going to be nothing but a vector plus b vector in case I'm doing addition. Now we can write it in terms of their components. I will get ax I cap plus ay j cap, put the brackets here, plus bx I cap plus by j cap. Now I cap and j cap are not subscript but rather normal alphabets that are there. So if I have a look at the magnitude of I cap and the magnitude of j cap, it is equal to 1. Now what we are going to do is, we are going to group the terms. So all with I cap will come together, the terms with j cap will come together. So I will use different colors in order to depict them. So this is my bracket, I'll have my I cap plus the bracket and j cap. So I will have ax I cap and ay j cap. So what have I done? I have grouped the terms. So bx, by. So you can see that I have all the x terms with the I caps together, all the y terms with the j caps together. And this is nothing but rx I cap plus ry j cap, which is equal to r vector. The magnitude of r vector is going to be root of rx square plus ry square. So this is what we have done as of now. We have grouped the terms analytically and we have put them all together. So I can go ahead and I can even find what is the unit vector. I already have I and j, but if I have to find the unit vector for r, that is in terms of r cap. R cap would be equal to what? R vector by magnitude of r vector, which is nothing but rx I cap plus ry j cap divided by root of rx square plus ry square. Now this we have done it along the x-axis, or let's say for two vectors, that is along the x and y axis. What if we have 3 dimension? So this was for 2 dimension. Now the same concept can be utilized. So if I take a vector as, let's say, ax I cap plus ay j cap plus az k cap, b vector as bx I cap plus by j cap plus zz k cap, and let's say c vector as cx I cap plus cy j cap plus cz k cap. Now the only thing that you're going to do is you're going to add them up like this. So since I've written it one below the other, all the I caps you're going to add, all the, let's say, coefficients of j cap and coefficients of k cap. So when I tell add, you will simply write it like this. That is, the resultant vector is nothing but a vector plus b vector plus c vector is equal to ax plus bx plus cx I cap plus bx, no, it will not be x, no? So this one was cx I cap, all the y's. So I'll have ay plus by plus cy of j cap plus az plus bz plus cz of k cap.